DeepSeek just released its latest model. This new model delivers state-of-the-art performance across a broad range of benchmarks. But the real story is its remarkable long-context efficiency. Compared to the previous DeepSeek V3.2, the new model dramatically cuts inference compute and memory. Let's see how its new attention design makes this possible. When a transformer model processes a sequence of tokens, each encoded as a d-dimensional vector, the attention mechanism enables the model to capture context and build a richer understanding of the sequence. But this creates a major challenge. Memory usage grows linearly with sequence length. Typically, each embedding vector has a dimensionality of several thousand. But the sequence length can easily grow to millions. Let's first briefly review the standard attention mechanism to set the stage. The attention layer uses query, key, and value matrices to linearly project each hidden state into query, key, and value vectors. We compute the attention output by taking a weighted sum of the value vectors, where the weights are determined by the scale dot product between each query and key vector. This process produces a c-dimensional output vector for each token. Therefore, we use an output matrix, WO, to project the output vectors back to the same dimensionality as the hidden states. This output matrix has dimension c by d. We then add these residual embeddings back to the original token embeddings to inject the contextual information. Self-attention allows the model to enrich each embedding with context from the entire sequence, ensuring that every refined embedding captures all relevant relationships and details. But relying on just a single set of query, key, and value matrices is insufficient to capture the full complexity of relationships between tokens. To address this, we introduce multiple sets of query, key, and value matrices, allowing the model to learn and represent a diverse range of relationships between tokens. This is achieved by expanding the query, key, and value matrices to include multiple attention heads. Here, H is the number of heads. We show 4 heads in the illustration, but in practice, the number can be much larger, such as 128. We split the query, key, and value matrices into edge heads and compute attention for each head separately. This gives us a collection of attention outputs O1, O2, O3, and O4. We concatenate the outputs of the multiple heads together and use our output matrix WO to produce the residual embeddings delta H. This is known as multi-head attention. Let's now visualize this more concisely. In standard multi-head attention, during inference or decoding, we must cache the key and value vectors from all previous tokens. Therefore, the total key value cache memory is 2 for keys and values, times the head dimension, times the precision in bytes, times the number of heads, times the number of layers, times the sequence length. This is a lot of memory. How do we reduce the memory cost? One simple idea is to reduce the number of heads for key and value matrices from H to 1. In this setup, we generate just a single set of key and value vectors for each token. The key and value vectors are then shared across all attention heads. This approach is called multi-query attention, or MQA for short. Let's compare the memory requirements of MQA with the standard multi-head attention. Multi-head attention requires 4 megabytes of memory per token. In contrast, MQA requires only 31 kilobytes of memory per token. It's a 128-fold reduction in memory usage. However, there's a catch. By sharing key and value vectors across all heads, MQA reduces its ability to model nuanced relationships between tokens. As a result, MQA's performance degrades considerably compared to the original multi-head attention. This limitation has inspired several subsequent innovations, such as grouped query attention, GQA, and multi-head latent attention, MLA. But all of these methods focus on the number of attention heads. Instead, DeepSeek's new attention mechanism shifts the focus from the number of heads to the sequence length. So, how do we compress the KV cache along the sequence dimension? Here, we have a sequence of 16 tokens. Each token embedding is a 7,168 dimensional vector. We extract the key value information using a matrix WKV. This maps the d-dimensional hidden state to a lower dimensional vector we call a key value entry. In the DeepSeek V4 model, the dimension C is set to 512. The computation can be concisely expressed as a single matrix-matrix multiplication. Intuitively, not all tokens carry the same level of importance. Therefore, we can compress a group of key value entries into one. For example, by compressing groups of 4 key value entries into one, we achieve a 4-fold reduction in memory usage. But how exactly does this compression work? The simplest approach is to average the 4 KV entries. This works, but clearly it's not ideal. Information from an important token may be diluted by the other tokens in its group. To address this, we use data-dependent weighting. More specifically, we compute a scalar score for each token in the group using a dot product between its hidden state and a learned weight vector. We then pass the scores through a softmax function to obtain weights, S1 to S4. These weights determine how much each token contributes to the compressed KV entry. This allows the model to adaptively emphasize the most informative tokens within each group, rather than treating all tokens equally. The result is a compressed set of key and value entries that captures the most relevant context across longer sequences. But these key value entries are 512-dimensional vectors. Using a single scalar weight means that every dimension of a token's KV vector gets scaled by the same amount. Therefore, we generalize these scalar weights to per-dimension weights. More precisely, the model computes a distinct weight for each dimension across the 512-dimensional KV vectors using the softmax function. This gives the model fine-grained control over which features to retain, using a weighted sum with learned per-dimension weights, preserving more detailed information than simple scalar weighting. This element-wise multiplication can be more compactly represented using matrix notation. This matrix, which produces per-dimension scores before the softmax function, is denoted WZ. However, when we visualize the key value vector compression process, we notice that there are artificial boundaries between the compressed vectors. In other words, each compressed vector is formed from a separate, non-overlapping group of key value vectors. The outcome can vary greatly depending on how the tokens are grouped. To address this limitation, we incorporate overlapping groups of vectors, allowing each compressed entry to draw context from both its current group and adjacent groups of key value vectors. We first expand the key value vectors and the corresponding weight matrix for the previous group, so that each key value vector is included in multiple overlapping windows. For each overlapping window, we compute the per-dimension weights as before, obtaining a new set of softmax weights for that group. Each token's weighted key value vector is shared across overlapping groups, so its information contributes to multiple compressed entries. This overlapping compression scheme enables a smoother transition of information across groups, mitigating the harsh boundaries imposed by non-overlapping compression and better preserving important contextual signals throughout the sequence. We refer to this process as the token level compressor. Now we are ready to integrate the token level compressor into the attention computation. Let's start from the standard multi-head attention diagram. We first reduce the number of key and value vectors from H heads to 1. This is the multi-query attention, MQA. Next, we project each hidden state to a shared key-value entry using the matrix WKV. Then we compress the key-value entries across the sequence lengths using the token-level compressor. Like multi-query attention, the compressed key-value entries are shared across all attention heads. Thanks to token-level compression, each attention head can now use a higher dimensional key-value vector, 512 dimensions per head, instead of the typical 128 dimensions. But this poses additional computational challenges. For example, when computing the query vector, we need to transform the d-dimensional vector into a vector with c times h dimensions. Substituting in the actual parameter values, we see that WQ becomes an extremely large matrix. To make this more parameter efficient, we take a low-rank approach. We first project the hidden state H to obtain a compressed latent vector for the queries using a down projection matrix, WQ down. Then we produce the attention queries by up projecting the latent vector using the up projection matrix, WQ up. This low-rank approximation reduces the parameter count to just 15.8% of what would be required for the full WQ matrix. We also have a similar problem for the output matrix WO. To mitigate the substantial computational burden, we split the output dimension into G groups. Each group now has a dimension of C times H divided by G. We introduce a down projection matrix WO down, which maps each output group to a lower dimensional vector of size NG. Finally, we project the concatenated output to the final attention output using an up projection matrix WO up. This reduces the number of parameters to only 14.3% of the full WO matrix. We call this strategy grouped output projection. But even with token compression, we still need to calculate the attention between the current token and all preceding compressed key-value entries. This results in a slower tokens per second throughput. To fix this, we leverage a lightning indexer. The core idea is to efficiently score each compressed KV entry and select only the most relevant ones for the full attention computation. This selective mechanism is known as DeepSeek Sparse Attention, or DSA. Please refer to our previous video for a deeper introduction. By combining compressed key-value entries with DSA's sparse selection mechanism, we arrive at compressed sparse attention, CSA for short. We've skipped a few implementation details here. Let me briefly walk through them. When generating tokens autoregressively, in addition to attending to past compressed KV entries, we must also attend to tokens within a local window that have not yet been compressed. To prevent exploding attention logits and enhance the training stability, we apply normalization to each query head and to the compressed key-value entries. Like in multi-head latent attention, we apply rotary position embeddings to part of the query and key-value entry vectors. Finally, we introduce a set of learnable attention sync logits. These sync logits serve as dedicated entries that absorb excess attention mass, thereby encouraging more stable training. DeepSeek V4 also uses a complementary mechanism, heavily compressed attention, or HCA. Compared to the compression ratio of 4 in CSA, HCA compresses every 128 tokens into a single key-value entry. This aggressive compression not only dramatically reduces the size of the KV cache, but also enables the model to efficiently aggregate information from extremely long sequences. By summarizing large spans of tokens into compact key-value summaries, HCA allows the model to reason over much longer contexts without a proportional increase in computation or memory. Because HCA's compression is so aggressive, dense attention over all compressed entries is already efficient. No sparse selection needed. Together, CSA and HCA form a complementary pair. CSA preserves local detail through sparse selection, while HCA maintains broad global context through heavy compression. Let's zoom out to see how these pieces fit together in the Pro architecture. We start with the token embedding as inputs. Each transformer block contains an attention layer followed by a mixture of experts layer. The first two layers use HCA to build a cheap global summary of the entire sequence, letting information mix across long contexts before the model commits to fine-grained processing. In the middle portion of the model, the architecture alternates between HCA and the more selective CSA layers. This design enables the network to repeatedly switch between forming broad global summaries of the sequence and engaging in focused, high-resolution interactions. By alternating between these two forms of compressed attention, DeepSeek V4 incrementally refines its internal representations, efficiently shuttling information across multiple levels of abstraction without incurring the full quadratic computation at every layer. Finally, the last layer uses full attention to reintegrate everything at full token resolution. This recovers details that compression may have blurred, producing the most accurate output logits. This schedule balances efficiency with expressivity, early global context, mid-layer iterative refinement, and a precise final readout. I hope you enjoyed this overview of compressed attention. Thanks for watching, and I'll see you next time.